All right, y'all. This image that just disappeared, and it will hopefully reappear in 1 second. Okay, wonderful. This is like your most basic battery here. And this is our goal for today, is to understand this image, right? Understand the chemistry that's happening on the inside of a battery, okay? Before we get there, we're going to take a look at an oxidation reduction reaction that happens just inside of a beaker, okay? So these oxidation reduction reactions, this is what we started with last class. These are central to electrochemistry, all right? This is a reaction here where you take a strip of zinc metal, all right, we have zinc solid, that's our zinc strip here, and you're going to place it into a solution with copper ions, right? So we can use copper 2 sulfate, for example. Really, it's the copper 2 that's participating in the reaction. The sulfate isn't actually doing anything for us. Okay? And when this reaction occurs, we'll have an oxidation reduction reaction where our zinc is going from being neutral zinc to a zinc 2 ion, right? So it's losing electrons. And the copper is going from a copper ion to being solid copper, right? Which means that it has to be gaining electrons. And remember, we had a fancy word for this. Losing electrons is oxidation. So the zinc is being oxidized. And the other thing, our copper, is then being reduced. Okay? So again, in this reaction, we have our zinc losing electrons and the copper gaining electrons. Right? So if we like hop in our magic school bus and zoom on down to the atomic level here, what we're going to see is these zinc ions, or I'm sorry, these copper ions, they collide with that solid zinc. And when that happens, an electron is transferred from the zinc to the copper. All right? So that means that the zinc now becomes a zinc ion because it's lost its electron. So now it's floating around in solution. And the copper is now solid copper atoms, right? So visually what you would see as this reaction's occurring is our zinc is actually going into solution, becoming zinc ions. And you see this solid copper growing on that strip of zinc. This copper, as copper goes from being a copper ion to a copper atom, you actually see it starting to grow on as a solid there in our product. Okay? The other thing is copper ions are actually this blue color. So you can tell based on the color of our reactant and our product that they're being pulled out of solution, right? I'm losing that blue color as copper goes from being a copper ion to solid copper on my product side. Okay, so again, there's this transfer of electrons that occurs from solid zinc to our copper ion when they collide with one another. All right. So why is copper able to take these electrons from zinc? All right, each element, or more specifically, each half reaction has what's called a potential. All right, we can call it an electric potential. All right, and how we're going to think about this potential is it's this pull of electrons, right? So copper is just stronger than zinc. It's got a better pull of that electron onto itself. So the copper ion is able to steal those electrons away from the zinc, not the other way around. Okay? In terms of units, this potential is measured in volts. All right. Let's talk a little bit more about units here. A very important concept in electrochemistry is charge, right? Those negatively charged electrons are being transferred. Charge is measured in units of coulombs, which I don't remember how to spell. I think there's a U in there. Which is abbreviated C. Okay? So you can measure, for example, the charge of an electron in the units of coulombs. That's the units that we use for charge. What's called the amps or flow of electrons is measured in coulombs per second. That's what an amp is. All right, and then this potential, this pull of electrons, is measured in volts, which is a joule per coulomb. Right, and remember, joules are what we use to measure energy. Okay, so again, why does this reaction occur? We're going to say that it's because copper has a greater potential, which means a stronger pull of electrons. Right? Those copper ions are going to steal those electrons away from the zinc because copper has a greater potential. Right? Wants those electrons more. Kind of think about it as a tug of war. Copper's better at it. Okay? So conceptually, I think it's not all that crazy to understand that when these two collide with one another, the one with the greater potential, the one with the greater pull of electrons is going to be the one that wins that battle, right? Gets those electrons. So our copper ions collide with those solid zinc atoms, boom, and then the copper is able to take those electrons, right? The crazy thing about a battery is that we have these same reactions that occur, but they're actually separated into different components. So what we're looking at here, our basic battery. On one side, we have our oxidation reaction. And on the other side, we have our reduction reaction. So just like before, we're seeing that our zinc is being oxidized and losing electrons. Our copper is being reduced and gaining the electrons. But these are happening in two separate vessels, two separate beakers here. All right? And these electrons that are being lost by the zinc are then flowing through this wire to the other chamber. Okay? So if we, again, hop in our magic school bus and zoom on down, we're going to see these zinc on this side, losing electrons, becoming a zinc ion. But those electrons are then going to travel up and through our wire here down to our other beaker where the copper is being reduced. right? The copper ions in that solution are accepting electrons and becoming copper atoms. Okay, so kind of the amazing thing about electrochemistry is like, yes, this idea of like this tug of war of electrons. Copper's stronger, it's got a greater pull for these electrons. So it kind of makes sense that copper would win when they collide with one another, okay? But this is also true even when they're separated in a different vessel, as long as those electrons have this wire here, this path that they can travel to. Copper still has that pull of electrons and can pull all the way from this beaker over here, right? So that's how we get electricity, this flow of electrons, is we have an oxidation reaction happening over here, a reduction reaction happening over here, and those electrons are flowing between those two vessels. Right, so our electrons are going from our oxidation reaction, right? Oxidation is losing losing electrons into our reduction vessel here. Copper's able to pull those electrons through that wire. All right, so fancy terminology. The place where the oxidation reaction takes place is what we call the anode of a battery. The place where the reduction reaction takes place, we call the cathode of the battery. So we see that electrons are flowing from anode to cathode. All right, this is this little phrase that I have stuck in my brain that helps me remember the direction of battery chemistry here, from anode to cathode. Okay, if you've ever used a battery, you see that they're marked with positive and negative ends here. Electrons are negatively charged. So which end are they going to be attracted to, the positive end or the negative end? The positive end. So the positive end is our cathode. Whoops. And the negative end is our anode, right? From anode to cathode. All right, so when you bust out one of those AA batteries and you got to put it in your remote control in a certain direction, that's because you need the electrons to flow from the negative end to the positive end. Okay, so again, we have this oxidation reaction happening in one vessel. These electrons are being lost because it's oxidation, all right? But they're traveling through this wire into our other vessel, our cathode, where we have this reduction reaction, our copper ions accepting electrons. So again, kind of the magic thing is that this pull of electrons that copper has, copper's better at tug of war, that'll occur through this wire. Okay? So if we zoom in here to our anode, again, we see that our zinc atoms are becoming zinc ions, right? So that means that our anode is actually like deteriorating as this reaction occurs. We're losing that solid zinc anode as it becomes zinc ions. So our anode loses mass as this reaction occurs. That's why batteries do not have an infinite lifespan. Eventually, you will use up your anode and your battery will no longer work. Right? It's slowly deteriorating over time. In contrast, our cathode, right, we have copper ions in solution that are becoming copper atoms, so our cathode is actually gaining mass as this reaction occurs. Okay, so then the last thing we got to discuss is this little thing in the middle. This is what is called a salt bridge. All right, and our salt bridge, what is it doing for us? Our salt bridge keeps our charges balanced. Okay, so it is filled with a salt solution, and its whole job is to make sure that our charges are balanced as this reaction occurs. Because remember, what's happening at our anode here is that neutral zinc atoms are becoming zinc ions. So I'm releasing a lot of these positively charged ions into solution as this reaction occurs. Okay? Nature is not going to allow us to have like an imbalance of charges. So the only way that this can happen, the only way that I can start dumping a bunch of positively charged ions into the solution is if they can be counterbalanced by negative ions. And so that's what our salt bridge is doing. We have this salt in our salt bridge. As these positively charged ions occur, it will start allowing negatively charged ions to flow into that solution. All right, help keep charges balanced. If we look at our cathode now, we have the opposite phenomena occurring. Now we have a bunch of positively charged ions that are being removed from solution. Right? So this is going to cause this charge imbalance, and our salt bridge is going to come to the rescue and replenish that supply of positively charged ions. Okay? So in this case, my salt bridge was made of potassium nitrate. Any sort of just very soluble salt will do. Okay? And again, the whole point of the salt bridge is just to help keep your charges balanced. On one side, you're creating a bunch of positive charges, so you need to counterbalance that with negative charges. On the other side, we're removing a bunch of positive charges, right? So then we'd have an imbalance with too much negative charge. So that's why we're going to add positively charged ions. Keep those ions balanced in our beakers. Okay? So here is our battery here. Let me get rid of some of my marking so it's not overly confusing. Okay. Again, we have oxidation taking place at our anode. So electrons are being lost at the anode. They're flowing through this wire towards the other end, which we call the cathode, where the electrons are being accepted. Okay. Our anode is then losing mass as this reaction occurs, and our cathode is gaining mass as those ions in solution become atoms. Okay? Now, obviously, we've all seen a AA battery before. It doesn't look like two beakers together, right? But it's this exact same idea, just kind of compacted into this tiny little form. All right? This is the same basic principle that's true for all batteries. You have oxidation reaction taking place at one end. Those electrons are flowing to the other end where a reduction reaction is occurring. Okay? So we have this special way of summarizing the contents of a battery using what's called standard cell notation. All right, and cell is a word that you hear a lot when talking about batteries. All right, cell is a fancy word for battery here. All right, so for this particular battery, our standard cell notation, and this is where the states of matter are going to be important. We got to include that in our cell notation here. Solid zinc. Okay? because we're going to start our standard cell notation with our anode material. Our anode is made out of solid zinc. And then you draw a little bar. All right, and in your next position, you put your anode solution. All right, in this case, our anode is in a solution of zinc ions. So that's what will go in this next box. Zinc 2 plus AQ. All right, so we have like the contents of the anode end of our battery summarized. First, the anode material, and then the solution that it's in, all right, separated by a bar. And now we're going to draw 2 bars. And in our first box, we put the cathode solution. Which is in this case those copper ions. That's at our cathode. Rather, that's in solution at our cathode. Okay, and then another bar. And on this side, we're going to put our cathode material. And what was our cathode made of? The solid copper, right? Cool. Okay, so we can summarize the contents of our battery using this standard cell notation, where we sort of include what the cathode's made of, what solution the cathode is sitting in, what the anode is made of, and what solution the anode is sitting in, right? All that information summarized in this standard cell notation. Okay? All right, let's take a look at another battery real quick. Same sort of basic structure. I got different reactions powering this battery, a different oxidation and reduction reaction powering this battery. I want everybody to take a second and see if you can identify which end should be our anode and which end should be our cathode. I shouldn't have told you which one the oxidation and reduction reaction is. All right, so look, how do I go about thinking about this? The 2 things that I remember that help me remember which is which here is LEO, the fact that losing electrons is our oxidation reaction. All right, that means that gaining electrons is our reduction reaction. And then the other phrase that I say to myself is from anode to cathode. All right, if you can remember those 2 things, well, that means that my oxidation reaction is what's losing the electrons. Right? So that means that the electrons start at my anode and they flow to the cathode. So my reduction reaction takes place at the cathode. All right, so in my mind, I can kind of get there from remembering these 2 things, whatever you need to do, but that's kind of part of the battle that we're going to be that you're going to be tasked with here. right? Remembering which end of your battery is your anode and which end of your battery is your cathode, given your half reactions. Okay, so I'm going to summarize the contents of this battery using our standard cell notation. Okay, I want everybody to start this off for me by doing the anode side. All right, the cathode side we're going to have to learn a little something new for. But for these first two boxes, you should be able to summarize the content of the anode using that standard cell notation. All right, so again, in that first box is our anode material. What's our anode made out of, right? And so that's going to come, right? So this is this solid iron. So notice that this is the reactant of our oxidation reaction, right? That's what our anode is made out of. Our anode solution are those iron 2 ions. Okay. So this one we should be able to do just by analogy of what we saw in our previous battery. All right. If we look at our reduction half reaction though, unlike before, if we look at our last battery real quick, my cathode was made out of copper because copper was the product of my reduction reaction. Okay? If we look at this battery, though, this one's a little different in that both sides of this chemical equation, my reactants are aqueous like I would expect, but my product is also aqueous here. All right, you can't make a cathode out of an aqueous ion, right? It's got to be some hunk of metal. So all of this reaction is happening in solution, but I got to have a way of delivering those electrons to the solution. And so for that, we're going to use an inert metal as our cathode, and a good default is just platinum. Okay? So the job of this platinum is to deliver electrons to that permanganate ion, turning it into the manganese 2 ion. All right, so we just need some sort of an inert metal to deliver our electrons. All right, if we do run into a case where we have all aqueous, we're going to default to this platinum anode here. So when I do my standard cell notation, I have all of these aqueous components in solution. Remember that first box is your cathode solution. So I'm going to have to list both the reactants and products of this reduction reaction. So we'll separate them with a comma. And the convention is to include the hydrogen ions or the hydroxide ions if this was a basic battery, but we do not bother to include water because water is always there. Okay, so I'm going to list all my aqueous components from both sides of my chemical equation. All right, because this reduction reaction happened all in solution. So then my cathode material, my last box, is that inert platinum. Okay. So the bottom line here when we're doing our standard cell notation is if the reaction occurs in solution, or I guess we can say only in solution, use an inert metal, which again, we're just going to default to platinum. What's called an electrode. So an electrode is an anode or cathode. What's up?
So say it was aqueous on both sides of the oxidation reaction, we would also use...
Yeah, you'd have a platinum anode on one side and a platinum cathode on the other side. Yep. Just something to help carry those electrons through that wire.
Could it be any metal?
It could be any inert metal. It can't be reactive, right? So platinum, so I guess just to be clear, inert means that it's not going to react with anything. I don't want it reacting with my solution and degrading or something like that. So platinum's like a great go-to. Probably pretty expensive. I don't know if there's a cheaper option, but yeah, platinum works great. Okay, so last thing we want to be able to, well, not last thing, but last thing we're going to do today that we want to be able to do for our battery is going to be to incorporate now our constants page for this chapter, this big ugly list here. Okay? So, let's just look here. Let's pick one. Where's the one that we just did like a million times? Here we go. Okay, so let's just look at one of these entries here. What's listed on this table is a bunch of half reactions. Okay? And then we're going to be using this table quantitatively, so we see on the other side we have this numerical value here, and this corresponds to that potential that we were talking about. Right? Remember, a potential is like the strength of the pull of these electrons. So we can take each one of these half reactions and assign a value to it, a potential value to it, which tells you how strongly it's pulling at electrons here. Okay? Now, notice in every single entry of these tables, see, these are all half reactions, but in every single one of these half reactions, our electrons are listed on the reactance side of our arrow, right? So this is a list of what type of half reactions, oxidation or reduction? Reduction. Oxidation's losing electrons, right? So electrons are on the product side of oxidation reactions. So this is a list of all these reduction reactions. Okay? And up at the top, is going to be the one, so they're sort of arranged in these in numerical order by the potential. Up at the top are the half reactions with the greatest potential value here, meaning they have a greatest tendency towards reduction. The best reduction reactions are listed up at the top. All right? So these are the ones that pull electrons the best. And the worst reduction reactions are listed down at the bottom. They have the lowest potential here. Okay? So again, this table lists these reduction reactions in order of greatest reduction potential, the highest potential, to lowest reduction potential. Okay? But what we saw with our reaction in our last battery, we had this zinc-ion reaction here, but this was our oxidation reaction. So how do I get my oxidation reactions? I just do the reverse of the reduction reactions that are written. Right? So the oxidation reaction at our battery was the reverse of this reaction here. We had solid zinc becoming a zinc ion and losing 2 electrons in the process, right? Oxidation's losing electrons. So if we want our oxidation reactions, it's just the reverse of what's listed on our table here. Because again, our table only lists reduction reactions. Okay? And there's this inverse relationship where things that are the best at being reduced up at the top are the worst at being oxidized, right? That makes sense. They want electrons. They have a greater pull for electrons. And the things that suck at being reduced, they have a really weak pull for electrons. Those are the ones that have the greatest oxidation potential. Right? So the best battery that you can have, the battery with the strongest reaction, will have a reduction reaction from the top of this list and an oxidation reaction from the bottom of this list. Right? That's going to be the best battery that you can get. Because at the bottom, these reactions are the best for oxidation. And at the top, these reactions are the best for reduction. Okay? So how the heck are we supposed to use these numerical values here? I'm going to take those 2 entries for our zinc-copper battery. All right. Our E0 cell, what's called our standard cell potential, is going to be equal to the potential at the cathode minus the value at the anode. All right, so real quick, going back to our battery image here, let's just make note. Our zinc was our oxidation reaction, right? So that meant that the reaction of the zinc occurs at the anode. And the copper was our reduction reaction, so that occurs at the cathode. So let's just make a note. Copper, this was our reduction reaction, meaning it takes place at the cathode. The zinc was the oxidation reaction, So that occurs at the anode. So we're going to take the value from our cathode, the 0.34, and we're going to subtract the value at the anode, that negative 0.76. Okay, notice that if we use this formula, we just pull the value from the table. We don't have to like flip signs or anything like that. That's actually already taking care for us. I don't know, that sounds weird. Anyways, you know what I'm saying. By this minus sign right here. So we're just going to take the value listed at the cathode and subtract the value listed at the anode. All right, so since we're subtracting a negative, we're really adding it. We get 1.10. And what are my units going to be? Not coulombs. Coulombs, this is now this potential, right? So this is this joules per coulombs or volts here. All right. If our standard cell potential is greater than 0, then our battery will operate spontaneously. All right, we will indeed have a flow of electrons from anode to cathode if our standard cell potential is greater than 0. If your standard cell potential is less than 0, that means that your battery will not react spontaneously, but non-spontaneously. All right, but remember, non-spontaneous doesn't mean it's not going to occur at all. It just means it's going to go in the other direction, right? So remember, non-spontaneous means it's actually spontaneous in the reverse direction, which from a battery standpoint just means that you botched which end was your cathode and your anode. You switched them up, right? Okay, so given our half reactions, we can figure out which one will occur at the anode and which one will occur at the cathode, and then we can look them up and use our formula for our standard cell potential here, where we take the value from the cathode and subtract the value from the anode. Okay. Now, spontaneous, non-spontaneous. What does that remind you all of? Delta G, exactly. And so what we're going to see next time, but we're not going to get into it here, is that indeed that standard cell potential is very closely related to the delta G of these reactions. Okay, so we'll finish up our battery discussion next time.